we saw how the Drude model shows how you actually get an average velocity for the charge carriers when you apply a field. So Drude gives a v drift. Let's think about what it's equal to, though. So we said it was sort of accelerating and then stopping, accelerating and then stopping, accelerating and then stopping. So the average velocity would be that acceleration times that tau, say. Okay? So the acceleration is, well, F equals ma, and the F is the charge times the electric field. QE equals ma. So the acceleration of a charged particle q in an electric field is just always QE over m. That's always the acceleration. You just have a charged particle moving. It's really just the force divided by the mass. So there's the acceleration, and then how fast it gets is tau. Right? It makes it up to tau time. So we have that expression. Now let's plug that into the microscopic current. So we said that the current, if you think of it as a flow of charged particles past some area, it depends on the density of the charged particles, how many there are per unit volume. It depends on their charge. It depends on the drift velocity, it depends on how fast they're going, and it depends on the area, the cross-sectional area of the wire. So all we have to do is plug in our Drude drift velocity in here for v drift. And we get it's n times q, and then it's q e over m tau. So there's v drift, and then times the area, like that. So Drude model into the microscopic current is like this, and then we can combine some things and move some things around, and what you'll see is we can write I over A, the current per unit area, that's what we called J before, that's the current density, equals, let's see, so we have N, and we have the charge squared, tau is there, all over the mass, and what we're left with is E. And you can see it makes Ohm's law. J, the current density equals something times E, and this something is the conductivity. So now the Drude model has given us a microscopic expression for the conductivity. Sigma, the electrical conductivity, not the surface charge density in this case, is N q squared tau over the mass. That is a conductivity. It's an ivity. That means it's an inherent property. It is an intrinsic property. It's not an extrinsic property. It doesn't depend on size or anything. It just depends on intrinsic things. Let's see if it makes sense to us. N, the volume density of charge carriers. Well, the conductivity should increase with N, yes. How much charge they carry? Yes, the conductivity should increase. How long they go before they collide? Yes, the conductivity should increase. And the mass in the denominator, that makes sense, because the lighter they are, the faster they'll move, the more mobile they'll be. So this is conductivity. Sometimes we use the resistivity, and that's simply 1 over the conductivity. It's m over n q squared tau. So those two we use sort of interchangeably. So you can see that Drude model gives you an answer that kind of makes sense. And if we worked out the units even work out as well. And I can see we have a question then about the Drude model. And MT knife, shouldn't the drift velocity be half of that? Drift velocity be half. Oh, yes, I know what they mean, yes. Yes, the drift velocity shouldn't be half. What they're referring to, and you probably saw this as well, is that we were plotting the velocity versus time, and we said, oh, it comes up and then it collides, and then we go up and bang, we collide, and we go up and bang, we collide, like that. And we were calculating the average velocity you get to if this is tau. So yes, the average velocity is actually down here. It's not this acceleration times tau, it's 1/2 of that. But if you look in a condensed matter physics textbook, This is the Drude model expression. And the reason is, a little trick in here, this isn't really how you define tau. That's 2 tau. The definition of tau is if you're in some point anywhere in time here, then tau is the average time from the previous collision and the average time until the next collision. So actually that's our definition of tau that makes a factor of 2 appear and disappear. But in the end, you get the same thing. So if you define this as 2 tau and you put in the half up here, same thing. So just to not create confusion, I just called it tau at the beginning. But for those of you watching every factor of 2, that's what's going on.